Good day. In this video, I will teach the step-by-step coding of Articulated Manipulator in Robotics Toolbox by Peter Corke for MATLAB online. Okay. So I have already created a script named articulated_sim.m. Okay, and already created each sections for our code. Okay, so our kinematic diagram is a kinematic diagram of articulated manipulator and its parametric table. Okay, so let's start by displaying the title. So articulated manipulator. Next are the sims. So in our kinematic diagram, we have three link lengths, A1, A2, A3, and three joint variable thetas. Okay, so A1, A2, then A3. So let's just name our theta T1, T2, then T3. In our link lengths, so let's just give 3 meters each. Okay, A2 is equals to 3 meters. Okay. Then A3 is equals to let's say 3 meters also. Okay. So unlike the prismatic joints, we don't need to put some joint variable value for joint variables here. Okay, at our joint variables section. So let's leave it blank. Okay, because our joint variable limit is from 0 to 360 degrees or 0 to negative 360 degrees. So it may start, the limit of our joint variable theta may start from the negative side up to positive side, or from 0 to the positive rotation, okay, or negative rotation to 0 rotation. Okay? So we don't need to put some values at the joint variable section, but we will use this T1, T2, T3 variables for future use. Okay, so let's go now to the DH parameters. So let's start at H01. So H0_1 is equals to link, close open parenthesis, square parenthesis, semicolon. Okay, so this is a revolute joint. So let's go to the parametric table. Okay, so if revolute joint, theta is equals to 0. D is equals to D. Okay, the value of D. So the value of D here is A sub 1 or A1, sorry. Then R is equals to 0. So we are at the first row. We are at the first row. So R is equals to 0. Alpha is equals to 90 degrees. So let's make it radian in terms of pi over 2. Then comma. So next is offset. Offset here is 0 because this is revolute. Then after offset, says here that after offset, put the value of theta. The value of theta here is 0 degrees. So we don't need to put the value of theta because it is 0, or just put 0. Okay, then the limit, so H0_1, the Q limit is equals to So, square parenthesis, semicolon. So, the limit, okay, the limit of the rotation of the first joint can be from the negative rotation up to the positive rotation. So, I can put here negative pi over 2 to, let's say, positive pi over 2. So negative pi over 2 is negative 90 degrees and pi over 2 is positive 90 degrees. Okay. Next, h1 underscore 2 dot q, sorry, dot q limit. h1 underscore 2 is equals to link. So open parenthesis, square parenthesis, then semicolon. Okay. So row 2. So theta is 0. D is equals to 0. R is equals to A2. So we have a value for R. Alpha is equals to 0. Our offset is equals to 0. The value of our theta is also 0. So let's make this 0. Okay. Then enter. So h1 to the q limit is equals to square parenthesis semicolon. So let's also decide that this will be from negative pi over 2 to pi over 2. Okay. So this is the second joint. Okay, this is the second joint. This is the second joint. Or this is the second joint. This one is the second joint. Okay. So if you notice, this is the 0 degrees. Okay. This is the 0 degrees of this mechanical manipulator. Okay. The origin position of the mechanical manipulator. Okay. So this, what we drawn here at our kinematic diagram is the origin position. So it means that theta 2 in this position is 0 degrees. So if we have here a rotation like this here, this will be the positive side and this will be the negative side. Okay? So in reality, these are mechanical components. So if we have here a negative 90 degrees rotation in our component, it will what do you call this? It will crash to the mechanical part down here. Okay, this link will crash at this mechanical part down here. Okay, so because this is in reality a robot, a real mechanical manipulator or robot arm, let's create an assumption that at the rotation downward, should not crush other mechanical parts if it's a real robot arm or mechanical manipulator. So instead of negative pi over 2, let's make it negative pi over 6 or negative 30 degrees. Okay. So next, h2 underscore 3 is equals to link. Okay, there is a syntax error. This is not link. This is link. Okay, link. Close open parenthesis, square parenthesis. Okay, let's go back to our parametric table. So, third link. Okay. Theta is 0. D is equals to 0, R is equals to A3. Okay. Alpha is equals to 0. Offset is equals to 0. Oh, sorry. Offset is equals to 0. So, after offset, you may put 0. Okay. The limit, okay, for each 2, 3, that QLIM is equals to square parenthesis again, semicolon. Okay. So, this is the third joint. Okay. In this part, if the link rotates upward or downward, it may not crash to other mechanical part of our mechanical manipulator in reality. So let's also put negative pi over 2 or negative 90 degrees, then pi over 2 or positive 90 degrees. Okay. So let's compile the links. So let's name a variable RT for articulated, then the function serial link, close open parenthesis, semicolon, inside the square parenthesis. So the links H01, then H12, then H23. Okay. Then after the square parenthesis, let's name our mechanical manipulator. So let's put some name. Let's just put the name RT. Okay. So RT is the string, not the name. Name is the command. So it's different here in MATLAB than Python. Okay. So sorry. Close open parenthesis. Then comma, add semicolon, sorry. Square parenthesis. So that's 3 joint variables at origin position. Comma, then workspace command. Okay, workspace. Then comma again. So the size of our workspace. So let's say our workspace is so our x-axis. Okay, x-axis. So let's say our x-axis negative 5. Oh no, negative 10 to 10. Then our y-axis is also negative 10 to 10. But our z-axis is 0 to 10. Okay. Then let's also put rt dot teach. rt dot teach. Okay. So F5. Okay, this is our articulated manipulator. Okay. So let's try to control our slide switches. So this is the first joint. Okay. So this is the positive 90 degrees. This is the negative 90 degrees. Okay. This is the positive 90 degrees and this is the 30 degrees. Okay. Let's see. Let's use the rotate if it will crash to the other part of our mechanic. Oh, it's not crashing. Okay, it's fine. Let's see. Wait. Okay, it's fine. It will not crash. Okay. In actual, okay, it's fine. So in actual manufacturing or actual prototyping, make sure your mechanical parts will not crash to each other. Okay. So that is negative 30. Then so third joint. So this is so let's put it at 0. Okay. So this is the third joint. So this is positive 90. This is negative 90. Okay, let's go back again to origin position. Okay, at origin position, let's see if our mechanical manipulator is the same with our kinematic diagram. Okay, so x-axis should point to right side. Okay, y-axis should point upward, then z-axis should point forward. Okay, so this is correct. Then the base frame or the zero frame. So x-axis to the right is positive. Okay. Y-axis backward is also positive. Then z-axis upward is positive. Okay. So this is our code for articulated manipulator in MATLAB Online, in a Robotics Toolbox by Peter Corke in MATLAB Online. So another tip, if you want to design a mechanical manipulator installed on a ceiling, okay, on a ceiling, okay, let's go back to our kinematic diagram. If you want to design a mechanical manipulator on a ceiling, just make the link length of that mechanical manipulator at the first link negative. Okay, so the first link is a sub 1, so let's make it negative. If we run this, it should be upside down. The articulated manipulator, okay, it's wrong. It's a wrong, sorry, it's a wrong code. It's the Cartesian sim. Okay, so let's go back here. Articulated, so let's test it at the Cartesian later. So let's make a sub 1 negative. Okay, a sub 1 negative. Then let's put some value at the size of z-axis. So this is negative 10. Okay, don't forget to change the size of the workspace because this will reflect, okay, at the negative side of the z-axis. So let's make the positive side 5. Okay, let's see if it will okay, so this is the mechanical manipulator at the ceiling. Okay, so it's not that good. Okay, so don't mind this black line. Okay, don't mind that. So let's try. Okay, it's still rotating. Don't mind that line. Okay. Oh, I forgot. This is still positive here. Okay. Because, okay, this is still positive 90. So, it will crash to the first link, the mechanical part of first link. But it's fine because this articulated manipulator is not designed to be installed at the ceiling. Okay, that's why we have here like this. It will crash to the link 1. Okay. But if this mechanical manipulator is designed for ceiling, there will be no crash at the mechanical parts. So let's see if we can edit it. We will edit it at the limit. Okay. So instead of negative pi over 6, so this will be the negative pi over 2 or negative 90 degrees. Then this will be the 30 degrees. Okay, pi over 6. Then also this. So this is fine. The link tree is fine. So let's CLC first, everything. Okay, negative 5 now is negative at our DH parametric table. So F5. Okay, so this is our okay. So this is now the negative 90. This is the positive 30 degrees. Then positive 9 sorry, this is positive 90, this is negative 90. So this is how you will make your mechanical manipulator designed if you will install it on a ceiling. Okay, so let's try it at the Cartesian manipulator. Okay, at the Cartesian manipulator, just change a sub 1 to negative a sub 1. Then let's put some value at the let's make the size of our z-axis 7 and negative 7 and 7, or let's make 7 3. Okay, negative 7 3. So this will be look like a Cartesian manipulator on ceiling. So this is a Cartesian manipulator on ceiling. Okay, this is how you will make your mechanical manipulator upside down. Okay, so that's for the articulated manipulator.